We had just begun chapter 9 on Monday, which is on fractions and fractional equations. So the main focus is, again, fractions in algebra, even though some of the examples I've included are non-algebraic situations, just to make sure we are all familiar with how to work with them. And I mentioned how in this chapter we have those specific sections to look at, and we started 9.1. We didn't finish it. So we'll see how much we can do today. So within section 9.1, let me go back to what that was, simplification of fractions. And on Monday, we looked at how to simplify these non-algebraic fractions. And I think everyone said you're okay with how to do this. Whether it's manually or, remember, you can even use the ABC button on the calculator, right? If you want to speed things up. Let's do another bit of recap. This is another kind of, this is an example of an algebraic fraction, but it's one that we have already looked at, or some of you might find this again, sort of review. We did something like this in chapter 2, how to reduce these kinds of fractions. Hey. Almost right. There are two mistakes you're making. So the 1 over 3 and the x part is fine. Pardon? The 1 over 3 and the x part is fine.
So the y and z is the problem.
Say again?
So the y and z are the problem?
Or at the, say that again, just the last part.
The y
and the z, yeah.
Is that the problem?
Yeah. I thought I heard you say a different word, which if you had said it, I would have said, yes, that's right. But you said problem, so sure, you're right. They're the incorrect, let's say, parts of your answer, but do you know why they're incorrect?
Why can't we reduce it down? Because they're underneath?
Yes. Yeah. So I heard bottom the first time around, and I almost said yes. Does everyone know what to do here? Yes. Okay. So I do want to point something out in this fraction, because what I'm about to point out is relevant for the next fraction and the fraction after. In this fraction, how many terms do you see at the top? How many do you see at the bottom? How many terms at the top? Just one? Yep. And at the bottom also just one. So in this case, you can go ahead and simplify the numbers, the x's, the y's, and, well, if I use a different color, the z's. So for the numbers, we get 1 over 3. For the x's, we get just x. And actually, I have another question. How many of you are using the laws of exponents here to work it out? Anyone using the laws of exponents? No? Interesting. If you were using it, I just want to show you something, because this way you can be sure of where things are. When you do x squared, when you're trying to reduce x squared over x, you can replace it with x 2 minus 1. Top exponent minus bottom exponent. And what I want to show you is this. When you do the same thing for y, the top exponent is 1, bottom exponent is 2, so it becomes that. And for the z, we have top exponent of 1 and bottom exponent of 3. So if you use the rules of exponents, and if you do top exponent minus bottom exponent, like the way I have shown it, the y and the z would be at this point at the top. Okay, that's something to keep in mind. But if you work out what we get here, yep, you'll get negative exponents. You get a 1 over 3 x, y to the negative 1, and z negative 2. And because we have negative exponents, we have to move these two bases from the top to the bottom. So final answer would be to say 1 over 3, or just x over y z squared. Is that okay? Any questions about that? This is not the only way to do it, of course. But if you ever have doubts about where the y and the z need to go, you can use the rules of exponents. You can also do it in a slightly different way. But rules of exponents are handy here. Here is another one. A common mistake I've seen before, previously, many times actually, is something like this. Is this correct for me to do? What if I cancel this x with that x? Is that correct?
No.
And why is that not correct?
Because the x is like the one x by itself is considered like a number-ish. And
Okay.
so you're taking it from the x squared first.
All right, okay. So in other words, one of the reasons why we cannot do this, and we can prove this if you were to sub in different values of x, is at the top, we don't have a single term anymore. We have two terms. At the bottom, we have one term, sure, but at the top, there are two terms. So because there's a plus or minus happening at the top, you cannot just simply cancel these two. So in this case, one thing we can do is what exactly to the top expression? Let's also use something we learned in chapter 8. Chapter 8 was all about, starts with an F, ends, yeah. Okay, so what's the most you can factor out here? An x, great. So we get x factored out, and you're left with 2x plus 1, and it's currently over 3x. So now, because we now have a product of two things, this being the first thing and this whole bracket being the second thing, now you can cancel out, let's say, this x with that x. Which is, in a way, what you said, by the way, Andre. But it's useful to see it this way because of what we'll encounter in the next example. So final answer here would be 2x plus 1 over 3. Let's take a look at 9.2. Multiplying and dividing fractions. Again, we'll talk specifically about algebraic fractions and what we can do here. I think I'll try skipping directly to this example just to see how much of you, how many of you can or know what to do here. The question or the instruction is to multiply and reduce the answer. And the two fractions we here are algebraic fractions. This is one of them. This is the second one. Do you know what the first step needs to be here? Any idea? Anything comes to mind? Yeah, go for it, Dark.
Get a single x value on the right side of it.
When you say get a single x value, what do you mean exactly? You could be right, but I just want to.
Because the first one doesn't have exponents on the x, you have to match it on the other side.
No. All right, so there is multiplication of two fractions. So one thing that you should keep at the back of your mind is the general rule involved when you're multiplying fractions. So let's say you have two fractions. The fractions could have any numbers on top and bottom. And let's say you're multiplying with c over d, for instance. How many of you remember the rules for multiplying fractions? Let's say just regular fractions, not algebraic. Pretend a, b, c, and d were just any numbers. Do we need to find common denominators here? No, we just do what exactly?
Cross.
When you say cross, do you mean a times d?
Yeah.
No. So if you meant top at top, bottom at bottom, then yes. So the rule that you should keep in mind, because you would have to apply it at some point in this situation also, is when you multiply two or more fractions together, you only multiply the numerators together, only the denominators together, always. So you could call it a cross, but don't call it cross, because then you'll think doing it this way. So the rule is you'll get the final product as AC over BD. Right? So we'll keep that rule in mind. That's the idea that we'll use here at some point. Now, if you were to do that right off the bat, if you were to take the numerator here and multiply with the numerator here, and denominator here with the denominator there, sure, you'll get a single expression. You'll get an answer with one numerator, one denominator. But the problem with that might be the reducing part. It'll be harder to reduce if you multiply first. So if you ever encounter algebraic fractions, you should always try to reduce first, then multiply. And the way to reduce first, then multiply is to factor as much as possible. As an example, the first expression, the first term, the first numerator, let's say, that's already, well, we can't really factor that much. Can we do something with the denominator? Can we factor this one? Nope. Okay, what about the numerator here, the x squared minus 4? What does that look like?
Squares.
Difference of squares, right. So we can apply a specific technique here. So factor using difference of squares, you're right. The bottom expression, the bottom denominator here, sorry, the second denominator, I mean, you could factor it in a way. You don't need to, but you can. So here's what the second step looks like. You would have x over x plus 2 in the first fraction, still unchanged, multiplied by, what is the factored form of x squared minus 4? Using difference of squares. Anyone? If you have it, I think you do.
X plus 2, x minus 2.
Perfect, thank you. X plus 2, x minus 2. That's right. I hope the rest of you also had the same thing. You just don't want to say it. And here's how you could factor this bottom. You don't have to, but if you really did want to, you could write x cubed as x times x times x. You could. And this way you should be able to see what, if anything, can be cancelled out. Can you all see it? How many things can be cancelled out? 1, 2, more than that? 2, okay. One of them is the x's here, any one of these. So let's say these two cancel out. The x plus 2 can also be cancelled out. So I'll take this and that. And just keep in mind, when you cancel out like this in multiplication, what's left behind here is a 1. What's left behind here is a 1. And now we can apply this rule. Once you've reduced as much as you can, apply that rule. To get the final answer, multiply the numerators together. So 1 multiplied by x minus 2 gives you an x minus 2. And over here we have 1 times the x times x. So x squared. And that'll be the answer in lowest terms. Okay, but again, the main idea is when dealing with algebraic fractions, factor all expressions if possible. Reduce or simplify if possible, and then any questions about that? Anything at all? Okay. Can I show you the next example? Marcello, you're okay? Sure. So, main difference between this example and the previous one is there's division. So let's take a quick look at let's recap the rules of division. If you have, let's say, any fraction being divided by another fraction, how many of you remember the rules here? Miguel, go for it. Right. As long as you also change the divide sign into multiply. Right. So the divide sign becomes multiplication, and your second fraction, and only the second one becomes, let's say, flipped like that. And then once you do this, your rules now are the same as for multiplication. So top at top, bottom at bottom. Now, again, we will apply this idea at some point, but something that we should do at the beginning is to try to factor whatever we can and reduce whatever we can. Actually, you know what? Let me actually change this into multiplication first. It might seem a little bit easier. So let's say we have x squared plus x minus 2 over x. And instead of divide, we now have multiplied by, or let me just replace that with a dot. Oh, weird. There you go. Thank you. And now we have x squared at the top and x plus 2. So here's the rule I was talking about. When you have a over b divided by c over d, so any two fractions in division, the first fraction stays the same, the divide sign changes into multiply, and the second fraction flips. And that's the rule, let's say, that I'm using at the start itself. The technical word would be the reciprocal, like you said. How many of you were also able to factor out this expression? What kind of technique could you apply here? Say that again, sorry.
I just removed as much stuff as I could, and somehow I got it.
Let me see, you removed as much as you could. Well, okay, so there's only one specific technique we can apply here. You cannot do common factoring here because there's nothing in common. But there are three terms, and is it a quadratic expression? Yes, the exponent here is twice as big as the exponent here, which is a 1. So you'd have to do the whole, we'd have to look for two whole numbers, negative or positive, whose product equals -2 and sum equals +1. So which two come to mind? 2 and -1. And because the value here, the number in front of x squared is 1, you can directly go into factored form, and you could say x plus 2 and x minus 1. You can directly do that. Multiplied by, I can write x squared as x times x over x plus 2. And this is where we now begin to cancel out stuff. But if you're not sure about this part here, let me just blow this up a little bit more. Note x squared plus x minus 2 is a this a refers to the first number, the number with the x squared term. B would be the number with the x, and c would be this number. So a equals 1, and the way to factor would be to find two numbers whose product is a times c and sum is b. A times c based on this is -2, sum is 1. And the two numbers that work are 2 and -1. So just a quick note for anyone who might be wondering. But if you know what you're doing, you can go directly from here to there in one step. Again, can you see some certain cancellations that can happen at this point? Yes. Okay. And so cancel as much as you can. The x plus 2, for instance, with that x plus 2. And the x with that x, one of those x's. And final step would be to just clean this up a little bit. numerator times numerator, denominator times denominator. At the top we have x minus 1 times x. So it's better to write the x first and then x minus 1. At the bottom, what do we have? Just 1, yeah. There's a 1 over here, there's a 1 over here. So you could say it's over 1, or you could just say the answer is x times x minus 1. A question I've been asked before is this. When you are, let's say, answering questions like this, when you get to this stage, do you need to multiply these two brackets? Well, the x, let's say, into the bracket, and my answer is no, you don't have to. You can leave it in, let's say, factor. We did the same thing here. In the previous example, actually, we didn't need to do it. But if there was something else left at the top, let's say another bracket, you could just leave it in factor form. You don't actually have to multiply it out. Any questions about this example, or can we keep going? Anything at all? Not yet. Okay. So let's take a look at addition and subtraction of fractions. And in this section, we'll start with just regular fractions, non-algebraic fractions, and then we'll apply the same idea to algebraic fractions, how to add and subtract them. So let's see. Let me again jump to an example because I think, and you can prove me wrong, I think you may have an idea of what to do here. 4 fractions in addition or subtraction. No algebra there. They're not algebraic, let's say. Does everyone remember the general idea here? To add them? Add and subtract? Someone said something, sorry. Common, okay. Now, I do have a question about that. You said find the common denominator. Would you work with this 2 at a time or something? You can do all of them. And that's what I'd like you to do. If all of the fractions are in addition or subtraction, you can find the lowest common denominator for all of them. Some of you may call it the lowest common multiple. That works too. Same idea. Now, my next question then would be, how many of you know how to find the lowest common multiple? Or lowest common denominator? Do you know how to find it? It's basically, you have to look at the denominators here. Okay, so you're saying the lowest common denominator here is 12. You're right. Now, can everyone think of the correct LCD here, lowest common denominator? 12 is the answer, but can you all see why it's 12?
Yep.
Yes? Would you like to know one usually quick trial and error way of finding LCD? It's again, it's usually very quick. What you do is this. First of all, we only need to look at the denominators. So here's a quick way of finding LCM. Quick trial and error method to find LCM. So first thing we have to do is identify between these 4 denominators the biggest number, which we can all agree is 6. Okay, so 6 is the biggest, let's say, denominator there. That's the first step. The second step would be to ask, can the remaining denominators divide into 6 nicely? So does 2 go into 6? Yes. Does 3 go into 6? Yes. But does 4 go into 6? No. So because we're getting a no from one of them, 6 is not the LCD. 6 is not the lowest common multiple. However, if you still stick with 6, find the next multiple of 6 that can be divided by all of them. So we already tried 6 times 1, which is 6. It doesn't work. If if you just do 6 times 2 now, you get 12. Just check if 12 can be divided by all of them. 2 goes into 12, 3 goes into 12, 4 also goes into 12. So it turns out LCM or LCD, whatever you want to call it, equals 12. It's a trial and error approach. There's a proper way of finding LCM also, but I won't show that here, not yet. Not unless you ask for it. Most of the time this is good enough. This method will give you the answer most of the time. So, okay, we found the LCM, and do you remember what happens next? What would you do in the next step? Just as a quick, go for it.
Like write out all the denominators as 12.
Perfect.
What you did to get to 12
Yep. So in other words, the whole point of finding the LCM was to change each of these individual denominators into the LCM. And then because each fraction is getting a new denominator, you'd have to think about how the top number must also change so that the value stays the same, the value of the fraction. So 4 times 3 is 12. So you got to do the same thing at the top over there. 6 times 2 is 12. Do the same thing at the top. 2 times 6 and 3 times 4. And this way you get new numbers at the top. We get 9 and 2 and 6 and 8. And now you can add and subtract as you see them. So final answer would be over 12. 9 plus 2 is 11. 11 minus 6 is 5. 5 plus 8, 13. Right? I will never again go through this in so much detail. Only because when you have questions like this, the 3 over 4 plus 1 over 6 minus 1 over 2 plus 2 over 3. Number one, you'll never encounter that specific. You'll never test it on this idea. This example is more as a way of recapping. Number two, you can actually use your calculator to work this out also. And that's also a skill you should have. So my second question is, do you know how to do this on the calculator? Using the ABC button. All you have to do is 3, so numerator ABC 4 plus numerator ABC denominator minus numerator ABC denominator plus numerator ABC denominator. You can type in the whole thing and press equals, and most likely, depending on what your calculator is set to, it'll show you this answer, the mixed answer, the mixed form, the mixed number, I mean. So it's worth trying if you ever have to work with fractions at any stage. In your other courses, you would maybe. Are you getting this, Marcello?
Yeah.
Yep. And you know how to switch from here to there, right? Manually or on the calculator.
From 13 over 12 to 1 over 12.
Sorry, I think, didn't you get this on the calculator though?
Yeah, that's what shows up.
Yeah. Do you know how to switch the calculator display to show you the 13 over 12?
Show you that?
Yeah. Just hit your shift or second button. Yeah. Or manually it would be like this. Your denominator will not change at all. To get the new top number, multiply these two. 12 times 1 is 12, and add the 1. Get 13, right. But again, I want everyone to be able to do this manually or using the calculator. I'm going to assume you can do this also then. Okay. The only thing that I should probably make sure of, whether you're doing this manually or on the calculator, is really, really simple. Just use the ABC button 4 times. Well, actually 3 times. 8 ABC 3 ABC 14 is enough to enter the first number, minus 3 ABC 1 ABC 3 is enough to enter the second fraction, and so on. You won't need the ABC button here, and then you can enter this way also. But if you're not doing it using the calculator, then you would have to change, or I would recommend changing each mixed number into improper fraction. working with them manually. So I'll just show one step just to make sure everyone can. Each of these mixed fractions, they will still have the original denominator at the bottom. So this is still going to be over 14. This one's still going to be over 3. The 2 is still a 2. And the last one will be over a 7. But does everyone remember how to get those top numbers? Yes. So 14 times 8, and then plus 3. What is 14 times 8? 112, and then 112 plus 3, 115. I'll just write it over here. And over here we have 3 times a3 plus 1. We have 7 times a1 plus 4. And just to write this part out, 115 you said over 14 minus a 10 over a 3 minus 2, which you could say is over 1, and minus 11 over 7. And from here, just evaluate on your own further. But again, I have nothing against you using the ABC button if you see fractions like this. Can we go on to an algebraic fraction? You'll see a few things when you start dealing with algebraic fractions. One of them is that you won't be able to use the ABC button anymore because it won't be useful anymore. One of the main skills here, now that we're dealing with algebraic fractions, is to be able to correctly identify the LCM or LCD, and then use that to do what's being needed, what's being asked here. The question is to, well, it says combine, sure, but we can all see there's a subtraction between two fractions. So the question really is to subtract those two fractions. So in the final answer, how many fractions would you get? 1, yep. Just like here also, in this example also, you'd get a single fraction. Here also, you'd get a single fraction. So we do expect to get, or we should expect to get a single fraction, no matter how many algebraic fractions you're adding or subtracting. The final answer would be a single one. Question is, how do you proceed? How many of you know what to do to find the LCM? Clearly their denominators are different, which means we cannot just add the tops together or subtract the tops together. Does anyone have an idea how to find the LCM here? In this case, sure, that works out just fine. It works out just fine in this case, yeah. But sometimes, if you cross multiply, and let's say you had 3 fractions, you might end up with a common denominator, but not the lowest one. And because it's not the lowest one, you'd have to reduce later on. So, well, let me give you an approach. Here's one approach you can use. It kind of really tries to break it down. When you get good at this, you won't need to use the approach I'm showing you. You can just work it on your mind. But the approach you can use to find LCM, to find LCD or LCM of algebraic fractions. Let's just try to organize what you see in the denominator. The denominator has 2y here and an x over here. And the way I like to organize this stuff is, do you see, let's say, numbers? If so, list them. Do you see variables? If so, list them. And do you see polynomials? And if so, list them. We'll go through each of them. By numbers, I mean numbers like, let's say in this case, a 2. Numbers that are not part of polynomials. So there's a 2 over here. You could say there's a 1 over here. So I'll just write that out. There's a 2, there's a 1, And what is the LCM between 2 and 1? 2. Great. Perfect. I'll write that down. Or let me do this in blue then. 2. Let's list any variables we see. There's an x, there's a y. So we could say there's an x, there's a y. And the LCM of two dissimilar variables would be the product of those two. It's very easy to prove that, by the way. We can get into that if needed. But do you see any polynomials? Polynomials would be when you have many termed expressions. At the bottom, this is a single term, this is a single term. So there are no polynomials here. I could put a cross like that. So the overall LCM or overall LCD for the entire question is going to be the product of these two individual LCMs, which is what you'd get, by the way, Stefan, based on your own idea. Again, mainly because of the kind of situation you have. It won't always work, what you said. Here the LCD or LCM is 2 multiplied by xy, which is 2xy. So that tells us for each of these fractions, we need to have 2xy at the bottom. And then the question becomes, if the original denominator was 2y and the new one is 2xy, can you see what the top must be multiplied by? Yes. And the way you can answer that is, well, what is this thing missing to become that? X. So if you multiply this one by x, it means you have to multiply the top by x also. And what is this one missing to become that? 2y. Okay, so let's say, well, this one needs 2y, so we have to do the same thing up there. So x times x is an x squared, and 5 times 2y is 10y. Is that part okay? Yes? What do you think we should do now? Do you think we should reduce each fraction? Should we reduce each fraction? Or should we do something else? What do you think? So keep in mind we're trying to combine it into a single fraction. And if you did reduce these individual fractions, you'd end up at the beginning again, because this reduces to that, this thing reduces to 5 over x. So our goal is to combine, to go from two fractions to a single fraction. So here's the final step. The denominator is 2xy for that single fraction, and at the top you have x squared minus a 10y. Can we subtract these two terms? No. That's because they are not like terms. They have different variables. So this is the answer. That is the single fraction. Currently, this first number here is over 1. And between 1 and any other number, the LCM would be the other number. So you could write this as something over 2x plus this over 2x. Can everyone see what the new top number is going to be here? 2x cubed, yeah. And that's because the 1 over here is missing, or it needs to be multiplied by 2x to become 2x. So we're going to multiply the same thing at the top, and you get 2x cubed. Does the second top number change? No, it stays as a 5. So the only step now here is to write it as a single fraction. 2x cubed plus 5. And once again, just check to see if you can do something more. They are, again, not like terms, so you can just stop there. Is that also okay? So So here's the next example, which is not as simple. Or maybe it is. You can tell me. To find LCD, let me again do this. Numbers, variables, and polynomials. First thing you should keep in mind, and this is a good example for me to mention it more clearly. When we talk about numbers and variables, we're talking specifically about numbers and variables at the bottom that are not part of polynomials. So for instance, do you see variables here at the bottom? If I were to circle these two? Yes? You'd say x, right? But is the x part of a polynomial?
Well, let's say 3x.
And which might bring me back to the idea of polynomials. Remember, polynomial means something that has many terms. So let's say 2 or more term expressions. Would you agree that x minus 3 is a 2-term expression? And 3x minus 2 is also a 2-term expression? Yes, so they're both polynomials essentially, and both the x's and the 3 and the 2, for instance, the negative 3 and negative 2, and this 3 over here, they are all part of the polynomials of those. So in this case, there are no numbers, or let's say no free numbers, and there are no free variables. All the numbers and variables you see are part of these two expressions. So let's list out the polynomials. First of all, there's an x minus 3, and then there is a 3x minus 2. Those are the two different polynomials we see in that situation. And turns out, if you have different polynomials in a situation like this, the LCM of these two would be their product, would be just x minus 3 times 3x minus 2. Just like that. You don't even have to write it out. I mean, you don't even have to expand by foiling it. You can just leave it like that. It's less, let's say, complicated to, it's more simple to leave it like this. And in this case, once again, the overall LCD is just going to be the product of all the LCDs here. There's nothing here, there's nothing here. The only thing that matters is x minus 3, 3x minus 2. Again, main takeaway is this. If you see polynomials as denominators, and if they're different, then the LCD would be their product. That's the main takeaway. There's one additional thing I should mention, but I think I'll mention it at a slightly different place. Okay, so let's see. I'll actually keep that there. So each of these fractions now gets x minus 3, 3x minus 2 as its denominator. This one gets x minus 3, 3x minus 2. They both get the same denominator now. And now the question is, how did the old one change into the new one? What should we multiply this one by? Can everyone see it? How would this old denominator become this denominator? What is it missing? That's 3x minus 2, which means we got to multiply this, the first one, the first numerator by 3x minus 2. And the second one is missing the x minus 3, so we had to multiply the top here by x minus 3. So at the top here we have x plus 2 times 3x minus 2. And over here we have a 2x plus 1 times an x minus 3. And while at the bottom we don't have to multiply it out, the tops we do. We do have to use FOIL to expand this and this. So in the next step, you could have just a single x minus 3 over 3x minus 2. And whatever comes out of expanding both of these brackets, you could lay it out over here and combine like terms.
Would you expand the bottom to
You don't need to, no. You can leave it as factored, in factored. If you were to expand it, it's not wrong. But I guess it'll be just a little bit more work. Did you expand these two already? What did you get for the first one?
We just kind of did it. I got the n and 10 really. No middles.
Okay, all right. Okay, let's go through this
I
then.
skip steps.
That's fine, as long as
I think it's correct.
As long as it's correct,
5x
yeah.
cubed minus x minus 7, right?
So we get 3x cubed. Wait, did you do both of them?
Yeah.
Ah, I see. Okay. So you had the answer to both of them combined.
Yeah, combined.
Right. I won't skip those steps at the moment. But
I'm just lazy.
x times 3x is 3x cubed. X times negative 2 minus 2x. Then we get plus 6x and minus 4. That's just from the first one. I may need more space, so I'll do that. From the second one, we have 2x times x, which is positive, so let's do this in blue maybe. Wait, no one caught this. It's supposed to be 3x squared. Back to this one. 2x squared minus a 6x plus x and minus 3. That's what you should get from each of those expansions. And we have to combine like terms. So this whole thing, again, is over x minus 3, 3x minus 2. Combining the x squares, we get 5. Yep, 5x squared. There's a minus 2x plus 6x, and then there's a negative 6x plus x. So you should just get minus x and minus 7. That should be a final answer. Section 9.5. It's on fractional equations now. So far we were looking at multiplying fractional expressions, adding them, subtracting them, dividing them. But now we're dealing with equations that have fractions. And you know what? I think, again, I'll start with an example. And at least officially, I'd like to show you a single method that helps to get rid of fractions completely in one step. Yeah. Essentially, yeah, it's about getting rid of the... That's right. And we can do that because these are equations. So as long as you do the same thing to both sides, the equation is still balanced.
What if you move it to 15 to the other side?
So the thing is, you shouldn't have to, because
Well, in this scenario.
in this scenario you don't have to, because the x terms are already on one side.
But if it's not, then
Yeah. So some of you might have a solution for this equation that involves fractions at every stage. And if you get the right answer that way, that's still great. No complaints there. But if you'd rather have fractions eliminated after one step and then work with equations that have no fractions in them, then I would recommend the method I'm about to show you. In the method that I recommend, the first step is to identify, let's say, the LCM or LCD, whatever you want to call it, of all the denominators. So I'm emphasizing all because I want you to look at denominators on the left and the right side. In this case, what is the LCD? What would you say is the LCD here?
15.
15, yeah. Looking at the 5, the 3, and the 15, even if you use a quick approach, 15 is the biggest number out of those three. And the first check is to ask ourselves, do 5 and 3 go into 15?
Yes.
The answer is yes. So LCM of, let's say, 5 and 3 equals 15. Now, as soon as you find the LCM, here's what we do differently because we're dealing with equations. Instead of changing this to 15, changing that to 15, etc., instead of doing that, we are going to multiply everything on both sides by the LCM. Everything. So we had 3x over 5 minus an x over 3 equaling a 2 over 15. That was the original equation. And what step number 2 really means is to rewrite this as first fraction multiplied by 15 at the top, second fraction multiplied by 15 at the top, this fraction multiplied by 15 at the top. Even if you didn't have a fraction, whatever number you have, multiplied by 15 at the top. That's what the second step means. As shown below. And what you'll notice is as long as you've selected the right LCM, if your LCM is correct, before you multiply the 15 with the top, divide these two numbers. Do 15 divided by 5. Can you see that you get a nice whole number? You'll get, for instance, here we get, this becomes a 1 and you get a 3. Let's do the same thing over here, 15 divided by 3 first. This thing disappears and you'll get a 5. And 15 over 15, they both just become 1. So if you clean up this line, let's say, if you clean this up, you get a nice equation with no fractions. You get 3 times 3x minus 5 times an x equals a 2. And if you really want, you could even skip this step altogether and directly go into 9x minus 5x equals 2. Just by, right after you cancel like this, do 3 times 3x, you get the 9x. After you cancel like that, do 5 times x, you get this. And so on. Hey, question?
Yeah, I think you're moving too fast.
All right. Which is why I didn't skip the step, but which step are you not okay with right now?
The 15 right outside the bracket.
Okay.
So how did you do
You wouldn't get the 15?
No, I know how to get that.
Okay.
Uh,
How did I
5.
get rid of the 15 and have a 3?
Yeah.
Okay, all I'm doing is, as long as you know where the 15 is coming from, it's coming from 15 being the LCD, right? So the second step says, or in the second step what we do is, whatever you had in the original fraction, we had original equation, we had 3 fractions in the original equation. Multiply every single fraction, but only at the top, by the LCM. And that's what I'm writing over here, well, before it got this messy. What's happening after that is, before you multiply the 15 with the top, I want you to divide the 15 by the bottom.
Oh, it's 15 divided by 5.
Is 3.
Can you give me 3?
Yes. And 15 divided by 3 is going to be a 5. And 15 divided by itself is 1.
So it's division, right?
It's division. Yeah, I'm saying do division first. And if you don't want to speed it up there, whatever's left now, you can write out in a new line. So there's a 3 that's left over. So 3 times the 3x is left over here. Minus then a 5 times an x, and then equals 2. Is that okay? And now we just have the simple equation to solve for. 9x minus 5x we get as a 4x equaling a 2. So therefore x has to be that. let's at least find the LCM correctly for this one. And maybe get as far as finding the LCM and multiplying everything by the LCM to get something nicer at the end, a nicer form for the equation without fractions. And that's where we'll stop, and that's what we'll pick up from on Monday. Did you use the thing I showed you? Okay, all right. So let me use that too. To find LCM, there are numbers, or let's list out all the numbers, all the variables, and any polynomials. So first question: are there any polynomials at the bottom? No, which means there could be numbers, or any numbers that you see, or any variables you can see in the denominator you should consider. They are what you should list. So looking at all the denominators, there's a 3 here, there's a 1 here, there's a 2 here. Let me just list those out. There's a 3, there's a 1, there is a 2. And what's the LCM of 3, 1, and 2? 6. Perfect. Looking at the variables, do you have different variables? No, just an x and another x. So really you just have one variable. You only have to... Right. There's another situation, by the way. If you had, let's say, an x squared, you could list it as x and x squared, and then the LCM of these two would be the one with the higher exponent, if there was an x squared. But we don't have an x squared here. It's just an x, just one x. So here we just get x. And the overall LCM, or overall LCD, is going to be the product of these two, which is going to be 6x. Is that okay? Yeah. All right. So we'll stop here for now, for today, and we'll pick it up from here on Monday.